Imagine you are building this massive new feature, right? You've spent weeks optimizing the code. You test it locally. It runs flawlessly. And, I mean, it just feels like magic.
Oh, yeah. The best feeling in the world for a dev.
Right, exactly. But then you push it to staging. Your user walks into an elevator, loses cell service for like 10 seconds, and suddenly your entire application just completely loses its mind.
Just endless loading spinners.
Yes, it just freezes, waiting on a server that isn't there. And, well, that is the deeply frustrating reality of relying entirely on cloud-based artificial intelligence. So welcome to this deep dive.
Glad to be here for this one.
Tonight, we are tackling this massive architectural shift that's happening right underneath our feet. We're pulling from these great notes from the LLM Mastery series, specifically this module on trends in the future, which focuses on on-device AI or intelligence without the cloud.
Which is honestly a fundamental rewiring of how software is built today. I mean, for years now, the assumption has just been if you want genuine intelligence in your app, you have to rent it.
You just make an API call.
Right. You make the API call, you pay for the compute cycle on some massive power-hungry server farm out in the desert, and you just wait for the answer. But the industry is really hitting a wall with that approach.
Because it's fragile, right?
Exactly. Relying on a constant high-bandwidth connection to a data center introduces just incredible fragility into systems that are, supposed to feel ubiquitous and seamless to the user.
Yeah, and we're seeing this really clear trend away from that fragility.
Yeah.
When you analyze the limitations of cloud-only AI, network latency is, hands down, the absolute biggest bottleneck.
Oh, without a doubt, it's the killer.
And there's this fascinating detail in the source material we're looking at today. The documentation literally trails off mid-sentence when discussing this. It says network latency, milliseconds versus, and then it just stops.
I love that, an unintentional cliffhanger.
Right. But it perfectly frames the problem we're trying to solve. So unpack that for us. What does that missing comparison actually represent in real-world user experience?
Well, that missing comparison is really the core motivation for this entire engineering shift. When we talk about milliseconds, we are talking about the highly deterministic, single-digit latency of processing a request entirely on local silicon.
Like right there on the phone.
Right. The verses that got cut off, that represents the chaotic, completely unpredictable nature of the internet. We are talking about hundreds of milliseconds, sometimes multiple seconds of delay.
Oh, easily.
Because you have DNS resolution, you've got TLS handshakes, data physically traveling across fiber optics to an availability zone, hitting an API gateway.
Sitting in some server queue.
Exactly, sitting in a queue, waiting for a massive GPU to spin up, and then making that entire trip all the way back.
And as a developer, you have absolutely zero control over almost all of those steps. You can write the most efficient code in the world, but if the user's packet gets dropped on a congested cell tower, your app just looks broken.
Yeah, the user blames you, not the cell tower.
Always. It's like trying to compare cloud AI latency to local execution is kind of like trying to code in your IDE on a remote server with a terrible ping.
Oh man, that is the worst experience.
It really is. You hit a key, you wait a beat, the character finally appears. It just completely shatters your flow state.
Which is exactly why relying on the network is an unacceptable point of failure for the next generation of software. I mean, we are moving away from AI as a novelty.
Like a chatbot you just occasionally ask to write a funny poem or something.
Right, exactly. We're moving from that to agentic AI that is deeply integrated into the operating system itself. An agent that helps you navigate your phone or dynamically sorts your files or, augments reality through a headset in real time.
And for those applications, latency isn't just annoying. It literally breaks the illusion of intelligence.
It does. A truly smart system needs to operate at the speed of thought. And, well, physics dictates that you simply cannot achieve the speed of thought if your logic has to travel to Virginia and back.
So the motivation is super clear. We need speed, we need reliability, and local execution. But that introduces a massive physical constraint, doesn't it?
A huge one. Yeah.
Because we know that training and running large language models requires gigawatts of power and these warehouse-sized cooling systems. So if we are moving these massive neural network computations down to consumer hardware, why aren't these devices instantly overheating?
Right. Why doesn't it just catch fire?
Exactly.
Yeah.
How does a smartphone not melt its casing and drain its entire battery in 3 minutes?
So the answer lies entirely in specialized silicon. Over the last few years, dedicated AI hardware has been quietly integrated right into the devices we already own.
The stuff we're carrying around every day.
Yeah, we're talking about components like Apple's Neural Engine, Qualcomm's Hexagon NPUs, Google's Tensor TPU cores. These dedicated chips have fundamentally altered the power-to-performance ratio for consumer devices.
Okay, let me throw a bit of a developer-centric pushback at you here.
Sure, go for it.
As software engineers, we are, accustomed to compiling for general-purpose CPUs or offloading highly parallel visual workloads to GPUs.
Yeah.
Why should we actually care about the underlying architecture of these specific AI cores, like an NPU?
It's a fair question.
Because if a modern mobile CPU has incredibly fast clock speeds and all these performance cores, why can't we just optimize the code to run on the CPU we already have?
Well, because a CPU and an NPU handle computation in fundamentally different ways. I mean, think of a CPU like a highly paid, brilliant senior architect.
Okay.
It's designed to handle incredibly complex, sequential, heavily branched logic, the exact kind of dynamic control flow you write every single day.
Lots of if statements and loops.
Right. It can context switch rapidly, handle hardware interrupts, manage the entire operating system. But a neural network doesn't actually need a senior architect.
No.
No. A neural network is essentially one specific mathematical operation repeated billions of times. Matrix multiplication. It is just vast grids of numbers being multiplied and accumulated together.
So assigning a CPU to do that is just a massive waste of its general-purpose architecture.
It is entirely the wrong tool for the job. An NPU is essentially an army of interns doing basic arithmetic simultaneously.
I love that analogy.
Yeah. What an NPU does is strip away all that general-purpose flexibility of a CPU. It removes the complex branch prediction and the massive control logic, and instead, the silicon is densely packed with ALUs arithmetic logic units dedicated exclusively to multiply-accumulate operations.
Wow.
Furthermore, NPUs completely redesign the memory architecture. Standard CPUs suffer from the von Neumann bottleneck. They waste huge amounts of power and time just constantly shuttling data back and forth from main RAM.
Right, the bus is too slow.
Exactly. NPUs fix this by placing a massive amount of incredibly fast RAM directly next to the compute cores. The data stays local to the operation.
So the silicon is custom-built just for the math. And I think this highlights a crucial distinction in the life cycle of an AI model, right? The difference between training and inference at the hardware level.
Oh, absolutely. It's night and day.
Because training a model involves calculating gradients, constantly adjusting weights backward and forward, and moving just petabytes of data. That requires immense memory bandwidth and flexibility, which is why training remains securely locked in the cloud.
Right, you need the massive GPUs for that. But inference taking a pre-trained frozen model and passing a single user prompt through it to get a prediction, that is a highly predictable forward pass math problem.
You're just running the numbers through the existing maze.
Exactly. And because the math is so deterministic, the NPU can execute those operations with vastly less power per cycle than a CPU or, even a mobile GPU. That targeted hardware efficiency is exactly what prevents the battery from draining and the phone from melting.
Okay, so we solved the hardware bottleneck. The chips are capable. But even with an incredibly efficient NPU, we still have a severe software bottleneck, don't we?
We do. The models are huge.
Right, large language models are inherently massive. We're talking tens or even hundreds of gigabytes of weights. If you are designing an app, you simply cannot force your users to download a 40-gigabyte file just to run a local spelling assistant.
No one is going to wait for that to download.
Exactly. So to fit a massive neural network into a mobile device's highly constrained memory footprint, you have to shrink the software itself.
Which brings us to the compression toolkit. To make on-device inference viable, researchers have developed these really aggressive compression techniques. The two foundational methods we need to examine here are quantization and pruning.
Let's tackle quantization first. The standard mechanism here is reducing the precision of the model's weights from 16-bit floating point numbers down to 4-bit integers.
Going from FP16 to INT4.
Right. And to make this intuitive for developers, think about image compression. Quantization is remarkably similar to compressing a massive high-fidelity raw image straight from a DSLR camera into a lightweight JPEG.
That's a great way to picture it.
Because a raw file captures a massive spectrum of color data, far more data than the human eye can even consciously distinguish. So when you run an algorithm to convert it to a JPEG, you are intentionally throwing away some of that ultra-fine data. You are grouping similar pixels into the exact same color bucket.
Yeah.
The resulting file takes up a fraction of the space, But to the user looking at it on a phone screen, the picture basically looks identical.
That is a highly accurate parallel. In machine learning, a neural network is defined by millions or, billions of parameters or weights. Traditionally, during the training phase, those weights are stored as 16-bit floating point numbers.
Because you need the precision then.
Right. A floating point number gives you incredibly precise decimals, which you absolutely need during training to capture microscopic adjustments in the math.
Yeah.
But for inference, you don't actually need that extreme decimal precision to get a highly accurate prediction.
So we're essentially just rounding the numbers. We map those highly precise 16-bit decimals down to a grid of 4-bit integers.
Exactly. You move from a format taking up 16 bits of memory per parameter to one taking only 4 bits. Mathematically, that is an immediate across-the-board 4x reduction in the memory footprint.
That's massive.
It is. And it also yields a massive reduction in the memory bandwidth required to load the model into the NPU, which, frankly, is often the actual bottleneck for speed.
But, okay, my immediate instinct as an engineer here is skepticism.
Naturally.
If you drop precision that aggressively, like literally throwing away 75% of the data bits, doesn't the model become inherently stupid? If we go back to the image analogy, doesn't the picture just get entirely pixelated and useless?
Well, you would think so, but neural networks possess this fascinating structural resilience. Because these models are essentially massive distributed systems of probability, the knowledge of the network isn't stored in the ultra-precise decimal point of one specific weight.
Right, it's not a database lookup.
Exactly. The logic is distributed across thousands of interconnected weights. Dropping the precision from FP16 to INT4 acts more like adding a subtle layer of background noise to an image rather than deleting the subject of the photo entirely.
Oh, that makes a lot of sense.
Yeah, the aggregate probability across the entire matrix still points strongly to the correct answer. And since the NPU can process integer math significantly faster than floating point math, you get a model that is a quarter of the size, runs incredibly fast on local silicon, and retains the vast majority of its original reasoning capabilities.
Okay, so quantization squeezes the numbers. The second major tool from the notes is pruning, which is the process of removing unneeded connections entirely.
Yes, literally cutting the wires.
And my analogy here is a ruthless code refactoring session.
Oh, I like where this is going.
Imagine taking over a bloated legacy code base. There are thousands of lines of code, deprecated functions, and all these weird edge case error handlers that haven't been executed in 3 years.
We've all been there.
Right, so pruning is like running a static analysis tool that maps the actual execution paths and systematically strips out all the dead, unreachable code. You end up with a much smaller binary that does the exact same thing.
That maps beautifully to the architecture of neural networks. During training, a model forms a completely dense web of connections between its artificial neurons. Every node connects to every other node in the adjacent layer.
Just a giant spaghetti mess of connections.
Pretty much. But post-training analysis consistently reveals that a huge percentage of those connections are essentially inert.
Meaning their mathematical weights are so close to zero that multiplying them out has basically no meaningful impact on the final output.
Exactly the case. Pruning is the algorithmic process of identifying those mathematically weak connections and simply severing them. You are turning a dense neural network matrix into a sparse matrix.
But wait, if we are severing thousands of connections inside a highly complex matrix, don't we risk breaking the logic entirely? Like, how do we know which connections are genuinely safe to cut without integration testing every single possible output of the model?
That is the crucial engineering challenge of pruning. You can't just hack away at the matrix randomly. We use magnitude-based algorithms to evaluate the absolute value of the weights. If a connection's weight falls below a specific threshold, it gets zeroed out.
And the model just adapts.
Mostly, yes. The network often goes through a brief fine-tuning phase afterward to let the remaining connections adjust and compensate for the missing paths. By combining this technique with quantization, a model that previously required a dedicated server rack can now comfortably sit within the RAM of a standard smartphone without catastrophic forgetting.
Okay, so we have highly optimized NPUs, and we have models compressed down by 4x or more through quantization and pruning. But does this mean cloud architecture is completely dead? Is every piece of software just going to run locally moving forward?
Far from it. The future of software architecture isn't a binary choice between local and cloud. It is a strategic, highly dynamic division of labor. The practical standard emerging across the industry is the hybrid architecture.
The best of both worlds.
Exactly.
The source material we are analyzing clearly outlines this division. On-device inference handles the fast, private, simple tasks, while the cloud is reserved for complex, knowledge-intensive tasks.
That's the basic rule of thumb.
But let me ask a direct architectural question on behalf of the listener right now. If I am designing a new app tomorrow, how do I actually draw that line? How do I write the logic that decides what gets routed to the local MPU and what gets packaged into an API payload and sent to the cloud?
Well, you are going to be building orchestration layers. This is the core challenge for developers over the next 5 years. You need to build a lightweight routing classifier that evaluates a user's request in real time. And the primary variable that classifier needs to evaluate is privacy.
Oh, because if the data never leaves the device, you instantly bypass a massive security and compliance headache.
Exactly. That is the greatest advantage of local execution. If your application needs to summarize a user's private text messages, or analyze localized health data, or parse through their personal camera roll, your orchestration layer must route that request to the local NPU.
So the on-device model acts as a highly secure, instantaneous privacy shield.
Yes, it possesses all the highly sensitive personal context. However, if the user asks a question that requires broad world knowledge, for example, cross-reference my local calendar with the live flight delays for all airlines operating out of O'Hare right now, the local quantized model simply does not have that massive data set stored in its weights.
It's too compressed to hold live internet data.
Right. So the orchestration layer recognizes that knowledge gap. It takes the specific heavy-lifting query, strips out any personally identifiable information, and routes it up to a massive trillion-parameter cloud model that actually has real-time internet access.
The cloud returns the complex data, and the local model formats it into the UI.
You've got it. The cloud remains absolutely necessary for heavy computation. It is entirely about intelligent, dynamic task routing.
And understanding that hybrid architecture unlocks entirely new categories of devices, doesn't it? I mean, once developers perfect this routing on smartphones, the definition of an AI device rapidly expands out to the deep edge.
The edge is where things get really wild.
Yeah, we're moving far beyond laptops and phones to include industrial sensors, remote cameras, autonomous vehicles, and medical devices.
Because when you remove the requirement for a constant high-bandwidth server connection, the physical world really begins to wake up. Edge AI allows hardware that operates in completely disconnected environments to possess autonomous logic.
But I've got to push back a bit on the stakes here.
Okay.
Putting localized AI on my smartphone to draft an email is low stakes. If it hallucinates a word, it's annoying. But embedding heavily quantized AI into an industrial sensor, monitoring a high-pressure pipeline, or putting it in charge of an autonomous vehicle's braking system.
Yeah, the game changes entirely.
The stakes feel completely different there. It's not just a nice UX feature anymore. The margin for error just vanishes.
You are pointing out exactly why on-device execution is a critical requirement for these edge cases, rather than just a luxury. Consider the physical realities of the systems you just described. An autonomous vehicle moving at 70 miles per hour down a highway simply cannot afford a network latency spike.
Right.
It cannot wait for a TLS handshake to resolve before the vision model decides to hit the brakes for a pedestrian.
Milliseconds of latency versus a fatal crash.
Absolutely. And consider a smart medical device like an automated insulin pump or a next-generation pacemaker. Privacy is paramount, obviously, but guaranteed offline functionality is literally a matter of life and death.
Because if a patient walks into a concrete stairwell or a subway tunnel where the cellular signal drops completely,
that medical device cannot stop analyzing their vitals. On-device AI provides the deterministic, zero-latency, absolute offline guarantee that makes life-critical applications mathematically viable.
wow. It fundamentally changes how we have to calculate system reliability.
It really does.
Let's step back and summarize the architectural shift we've mapped out today. If you are writing software today, you have to move past the mindset of treating AI as just another remote API call.
It's so much more than that now.
You are now architecting for a landscape where you intentionally dodge network latency by targeting local MPUs and TPUs. You have to understand how models are compressed down by 4x via quantization and pruning, utilizing integer math and sparse matrices. And most importantly, your job is to build the hybrid routing systems that seamlessly orchestrate logic between a user's local memory and massive data centers.
It requires a completely updated mental model for latency, resource management, and system design overall. You are managing intelligence across a distributed spectrum now.
But as we wrap up this deep dive,
Yeah.
there is one massive unresolved variable regarding this shift to the edge that we saw in the source notes. As developers embed powerful autonomous models into the physical world, the question of governance becomes incredibly complex.
Oh, the legal side of this is a whole other beast.
Truly, the global effort to regulate this technology, the EU AI Act, various U.S. executive orders, China's algorithmic rules, they're all desperately trying to keep pace with engineering teams that are moving at light speed.
And those legal frameworks are really struggling to define accountability for edge devices specifically.
Which leaves us with a fascinating, pretty complex puzzle for you to ponder before your next sprint planning session. Imagine this exact scenario. A heavily pruned, highly quantized AI model is running completely offline inside an autonomous vehicle or a critical medical device.
Okay, high stakes.
The model encounters an edge case. The stripped-down logic fails, and it makes a critical error that leads to a catastrophic real-world result. Not a cloud outage, but a localized failure in the sparse matrix itself.
That's a terrifying thought.
Who is ultimately accountable for that failure? Is it the hardware manufacturer who designed the NPU? Is it the data scientist who decided to aggressively quantize the model to INT4 and threw away that specific fraction of precision? Or is it you, the software developer, who wrote the hybrid routing logic that decided that specific real-world task was safe enough to run locally in the first place?
That is a complex debugging nightmare right there.
It bridges the gap between raw code and real-world consequences. So keep that in mind the next time you drop precision to save a bit of memory. Enjoy the rest of your coding session, and we will catch you on the next deep dive.